Okay. Good morning. Good morning, everyone. Okay, so we're going to start our webinar, and this is the first of the. This is the first webinar of the webinar series that the UP system is going to to do for probably for many months because we're going to have a very long vacation, okay, of face-to-face, from the university. So today, what we're going to hear is a talk from one of the associate professors from the Institute of Mathematical Sciences and Physics, UPLB.
Assistants,
Sorry,
assistant professors.
assistant professor. Okay. um, he is currently doing his PhD at University of Houston in the USA, and he is part of the Financial Mathematics and Actuarial Science Research Cluster of UPLB. So without further introduction, we're going to start. But before that, I'm going to acknowledge the presence of our director, Dr. Edith Jose. Hi, Ma'am Edith. Nakamute yata siya. Okay. Anyway, we're going to start. So, Jeric.
Hello.
Hello, Ma'am Edith.
Hello,
Hello.
everyone.
Yes. And
Hello
also,
po.
yeah. And also for those people watching sa Facebook, you can put your comments in the Facebook page and or your questions, and then we're going to ask Jeric later. Okay. So let's start the ball rolling. Go, Jeric.
All right, sir. Okay. Good day, everyone. I will be talking about methods which are commonly used for stochastic subgrid scale modeling. All right, this will be a short talk and actually an expository. All right. I will leave some technical details. I will leave them out, but I will provide references if you want to dwell more on the theory. All right. So this is the short outline of my talk. I will start with presenting the parametrization problem. Okay. This is the same as subgrid scale parametrization in our context. So the problem is basically related to model reduction or model dimension reduction or coarse graining. So yeah, if you're working on those problems, then probably you know some methods that I might discuss today or illustrate today. And then after that, I will illustrate some methods and provide some notes. Just to be sure you can hear me, right? All right. Okay. So in the most general sense, parametrization is a process of taking into account the effects of unresolved processes, okay, in a reduced model. And so there might be some terms in here that you are unfamiliar of, like unresolved processes. So when we say unresolved processes, so by the way, I will discuss in the context of ocean, atmosphere, and climate science because this is a popular and important problem in that area. Although it is also used well for computational fluid dynamics and other related fields, but I will be talking them in the context of atmospheric science in particular. Okay, so back to unresolved processes. So just to explain a bit, when you say unresolved, okay, so they are either too complex. They are difficult to understand, or little is known about the process. That's why it's hard to incorporate them or represent them explicitly in a model. Okay, so instead of representing them, then what you want is just to have an estimate of their effects, and then incorporate that in a model, or in Actually, this one is more suitable. So either they are too complex or they are too small. So this is more suitable in this talk. If you can see the title is subgrid scale processes. So sub meaning they are smaller than the model grid size. Right. So they are too small relative to the special scale in which we formulate our model. So instead of decreasing the spatial scale or increasing the resolution of our model, we want to represent or we want to just incorporate their effects and not represent them explicitly. Of course, there are reasons why we want to do that, and that will be my motivation actually for this stuff. So in this slide, you can see a diagram showing you different atmospheric and climatological processes in various spatial scales and time scales. So in the horizontal axis, you will see the spatial scales. So in this diagram, they are actually the model domain. So for instance, if you look at the smallest scale, the turbulence, all right? So they are usually not represented because they are in Navier-Stokes, but they move right in a scale which is of order 10 to the negative 3 kilometers or even smaller, okay, to resolve them completely. Also, they are the fastest, okay, in terms of the temporal scales. So in the vertical axis, you have your time scales. And then what does this diagram gives you? So at the lowest or the smallest time scale and the smallest spatial scale, you have these processes. And as you go along and increase the spatial scale, these are the more important processes. If you are, say, studying or or modeling the atmosphere or global climate. So from 10 to the negative 1 to 10 to the negative 5, those are the domains for important atmospheric and climatological variables. Okay. Uh, but 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 the processes that evolves on a scale smaller than 10 to the 1 or 10 kilometers, they're also important. They're actually the processes actually contributes energy, okay, that affects the equation of motion for say hurricanes, cyclones, and even and even other important catastrophic phenomenon. Okay. So if you look at the highest time scale, you have the global circulation and climate variation. So if you're modeling, for example, climate change, then you want to use a model, okay, that moves or whose domain is the entire Earth, right? Entire circumference of Earth in 3 dimensions, usually columns, right, of the atmosphere is used for global circulation models. Okay. Back to the question, why don't we want to decrease the resolution to include those processes at small scales? There's only one problem, okay? We have a limited computational resource. And if you want, for instance, to model climate change, your problem is not only fine resolution, but you have to predict for long time, very long time, like decades or century. So with fine resolutions on a longer time, that would entail a lot of computational costs. And actually, to date, we can't do that if you're modeling explicitly. All right, say the turbulence. So in here are some known uh, um, multi-scale. There are not some known models for atmosphere and global climate. So DNS refers to your Navier-Stokes. So this is a numerical simulation of your Navier-Stokes, where turbulence is not is not estimated. If you increase the resolution, say you go to large eddy simulation, then this is an approximation or at least a physical formula, all right, to include the effects of turbulence. Again, what we are interested actually is at this level. So the global circulation model or the numerical weather prediction model size. So these are the grid size. So for instance, for global climate models, the grid size is around 100 kilometers. So imagine the Earth, and then if you want to make a model of the global climate, you need to divide the Earth in a box of size 100 kilometers by 100 kilometers, and we know that over that over the domain, there's a lot of processes that moves in a smaller space. Okay, so the measure on that box represents some sort of average of those processes. Okay, and those averages are influenced by small scale processes which are parameterized on a global climate model. So on the side, I just use, I think I mentioned this already. There is always a trade-off between computational cost and incorporation of underlying physics. So a modeler usually choose whether to dedicate the computational cost to make a finer resolution for the model. Then that would include more physics in the model, or reduce the computational cost by making a coarser mesh or coarser grid for the model. But then it would then decrease some of the physics in it and would increase empiricism or more reliant on data in terms of parameter estimation. Anyway, the bottom line is, okay, for models uh, that are formulated on a large spatial scale, the large scale models, okay, to save the computational costs, those processes that are smaller than the grid size, they are represented, and they're not represented explicitly, but their effects are estimated. And that process is called parametrization. Now, maybe to understand it more, okay, we formulate it in a language of differential equations. So in here, we have a coupled system. You have two types of variables. You have x as the resolved variables, and y are the unresolved variables. X and y can be vectors. They are not necessarily scalar variables. F and g can be vector valued functions, and h also. So f of x represents the interactions among the resolved variables. G of xy represents the interactions between your unresolved and resolved variables. Okay. And all right, h represents the dynamics of, or the evolution of your y variables. Okay. In some contexts, we call them slow and fast if we have separation of time scales. So if y moves in a faster scale than the x, or sometimes large scale and smaller scale if they have separation, scale separation, spatial scale separation, for non-essential and non-essential. I think this is used more in dimension reduction. Okay, so our goal is to find a system in terms of x alone. So we want to eliminate y per se. Okay, well, not really eliminate y, but incorporate the effects of the interaction of y with x in a model. So that our reduced model will be in terms of x alone. Okay. So how do we know if our reduced model is a good model? Okay. So depending on what we want our model to do. So sometimes we want our model to predict X. That means we have the same path or close path with X. So with the coupled system. So if you run the coupled system and if you run the reduced system, so if they show paths that are close to one another, then we say a reduced model is a good model. Or sometimes we are happy with the approximate stationary statistics. So if we know that our dynamics is stationary, then they have a long run statistics, the stationary statistics. So if their PDFs are close, probability density function, or they have the same decay of autocorrelation functions, spectrum, etc. Okay. So predicting X is like point-wise convergence. So you want to have the same path for X from the full model when you are solving it, and Y is solved explicitly and with the reduced model in terms of X alone. Approximating stationary statistics is like estimating climate. Okay? It will be run for a long time, and you want the coupled the X variable in the coupled system to have the same statistics with the X variable in the reduced system, even if they don't have exactly the same path. All right. So since you want a system in X alone, if you look at the coupled system, we want to replace G, okay, by some term or some estimate, okay. That is in terms of that can be solved using information about X alone, okay, without knowing what Y is. We refer to G as the subgrid term or unresolved tendency. So throughout the talk, I will refer to that term as subgrid term or unresolved term or subgrid scale term. All right. Okay. So how do we do that? So an obvious so one intuitive answer to that is just to estimate the mean, right? So if you estimate the mean of G and then replace G by its mean, then maybe a reduced system, okay, we work fine. But it's not the case mostly. Okay, we want more information. So we have what they call deterministic parametrization, where we replace the subgrid term by a function. So in here, that function is the small g, the small of g of x. So it is in terms of x alone, and with some parameters theta. Theta might be some parameters that arise when you include the underlying physics. So when formulating G, you can analyze what processes are involved in the subgrid process, and then estimate some parameters from there, include that in the function G, okay, together with the information from X. G can be anything as long as it's consistent. G can even be a network if you're working with in deep learning or machine learning. So deterministic includes conditional mean tendency. It's conditional because it is conditional on X. That is usually the case. It is conditional on the state of the resolved variables. It is rarely the case that it doesn't depend on the climate X. All right, or the subject of this talk, stochastic parametrization. So we can replace G. Ideally, we want the distribution. We want the distribution of G. Right? But stochastic parametrization only requires us to find a method in which we can draw samples from the distribution. So that means it is we don't need to know exactly the form or even some properties of the distribution. As long as we can draw samples from it, then we're good. Okay. we have a stochastic parametrization. But having an explicit distribution, or even more a stochastic process that represents G, makes our model useful for further analysis, for predictability, uncertainty, quantification, etc., etc. All right. Why do we want stochastic parametrization? Deterministic is often not realistic. Okay. Again, I will go back to its application in atmospheric science. That say if you have a grid box and you are estimating average temperature, surface temperature, okay, in terms of the temperature at smaller scales, okay. There is no one-to-one correspondence between the average temperature and the properties of the small scale or the subgrid scale processes. So given an x, there is no one g of x. That's what I mean. Okay? So it is not realistic. So variability with the of the subgrid scale processes must be incorporated. And maybe I will say that later. Okay, when we go to further notes. Do we have questions, guys? Before I proceed.
Do you have questions?
Should I answer or
we can entertain questions later, but I'm going to
okay?
acknowledge the presence of the director of the Institute of Mathematics of UP Diliman, Ma'am Kayen. Hello, and Mayang Mata from UP Mindanao. Hello.
Morning, morning. Salamat.
Morning po.
Morning.
Morning
Should,
to. I really like this topic. It's about stochastic. So carry on.
Okay, go
okay.
Jeric.
So so do you prefer to for me to finish first and then reserve the questions later?
Yeah, sige, ganun na lang. Go
All right,
Jeric.
sir. Okay. So then, because I will get technical from here, a little technical from here. So in the outline, I said I will illustrate some methods that are commonly used, right, for stochastic subgrid parametrization. So the first that I will illustrate is homogenization. This is similar to the to homogenization used for elliptic PDEs, for mixture problems, not mixture problems, for composite materials. Okay, finding effective properties of on composite materials. So now the example that I will use will come from this paper. This paper is data assimilation is low-fast system. So it does more than homogenization. So it analyzes data assimilation in the reduced model. But this one is a simple model. So that's why I want to use the model in this paper. Okay. Just a quick note, okay? Because we will use this one. All right, about generators. This is what you can see. That first equation is an SDE. dx equals f of x dt plus g of x dw. W is a Wiener process. That is your standard Brownian motion. Okay. So for every SDE, there's an associated operator and actually a system. I think it would be easier to go from the SDE to the backward Kolmogorov equations first. So you can formulate a Cauchy problem. Partial of b with respect to t equals f of x partial of b with respect to x plus g of x squared over 2. Second partial of v with respect to x with some initial value phi0, initial function phi0. Okay, V of x is expressed that way. Okay. So what? Oh no. Oh, yeah. Okay. Phi is some smooth functions. Again, I will leave the technical details. So just take it as is for now. Okay. What is important is an SDE gives you an operator. This operator. That operator is called the backward Kolmogorov operator. Okay. Inducing the Cauchy problem. So you can look at the SDE. Okay. Or its counterpart, backward Kolmogorov equations, and do analysis on either. That's the beauty of these generators. If you know more about the PDE, then you can make analysis on the PDE, and it will give you some properties that an SDE has. There is an adjoint operator related to L. The adjoint of L, which is called forward Kolmogorov, or in physical sciences mostly called Fokker-Planck operator, which gives you the Fokker-Planck equation. Okay. So the Fokker-Planck is more gives more sense because rho here gives you the density of the process X, okay, at time t actually, because rho is a function of X and t. Okay. So it gives you the evolution of density of an SDE. Okay. So why do I present this slide? Because we will do stochastic homogenization, not using the original system, not using an SDE, but using the operators and their associated PDE. Okay, so homogenization will be done in PDE, and then we go back to the once we have a reduced operator and the associated reduced PDE, then we go back to its associated SDE. So for stochastic homogenization, that's the common route. So from an SDE or even ODE. I forgot to write the ODE, but when you're given an ODE, then it's not called forward and backward Kolmogorov. They're called Louisville. I forgot the spelling. Louisville equation and then backward equation. Okay, for ODE. It is the same with these operators. Just drop the second term, and you'll have the Louisville and the backward operators for ODEs. Okay, so that's a common route. So you start with an SDE or an ODE, then you formulate its associated forward or backward Kolmogorov equations for Louisville and the backward equations, and then do homogenization for those PDE, and go back to an SDE or ODE, depending on the form of the operators. All right. So in the paper, they use this model. The model has three variables: x, y1, y2, y3. I reformulate the system and group the variables into slow variables and fast variables. You have the slow x variable and the fast y, vector y variables. Okay? So y collects y1, y2, and y3. F of x represents again the interaction of x with itself. Okay, why they're called slow and fast? Because of the small parameter epsilon. So epsilon controls the time scale separation of the system. The smaller the epsilon, the larger their time scale separation. Okay. So if you look at second, third equation for y1, y2, and y3, okay, and neglect the small parameter epsilon squared in the denominator, what you will get is a chaotic subsystem. Okay. Now it is the same as the system given in the model, just drop epsilon squared or set it to 1. Okay, you will get a fast chaotic subsystem. It is chaotic. If you're familiar with its form, you might notice that is your Lorentz attractor or Lorentz 63, the famous butterfly. Okay, solution manifold for the attractor. Okay, so that is a chaotic system, and it affects the evolution of x through y2. Okay, but y2 is coupled with y1 and y3. So technically, okay, all of the variables y affects the evolution of x. Okay, we will show that through homogenization, we can reduce it to an SDE. Okay, the difference between the SDE and the original model, of course, it is in terms of x alone, and that this term, okay, the subgrid term will be replaced by a stochastic term, sigma dw, and we will have a closed form for sigma later. Okay, so just to give you an idea, okay, the importance of this model in some atmosphere models. So this model is used for regime transition. The first equation is actually a double well potential. If you neglect the subgrid term, that is a double well potential. What is a double well potential? Well, if you set dx dt to 0 and then solve for x, you will have x1 minus x squared. Again, this is neglecting the subgrid term. It has 3 equilibrium, 0, 1, negative 1. 0 is unstable, 1 and negative 1 is stable. So that's why it's called double well. Something like that. This is 0, this is negative 1, this is 1. Okay, so if you start at say a number, so if the starting value for x is say a number less than negative 1, then it will be attracted to negative 1 and will not. Okay, and since this is a stable equilibrium, then it will stay there. Okay, and its density function later on will be just a Dirac function, or because it stays at negative 1. So if you start something larger than 1, then it goes to 1. Okay. If start at 0, then it can either go to negative 1 or 1, and then be there because 0 is unstable. Okay. So the subgrid term kicks it. Okay. It is kicked by chaotic noise. So instead of staying at one equilibrium point, it constantly shifts from negative 1 to 1. Okay. So that signals the regime transition. So this is a sample trajectory, okay, for 2000 model time units. So if you look at the values, so most of the values are clumped over numbers close to 1 and negative 1. Okay, and this is the stationary PDF. Okay, if you're not familiar with the PDF, think of histogram. So most of the data are close to 1 and negative 1. Okay, the next actually highest would be well 0. Okay, the depth of the well depends on the scalar or the small parameter epsilon. Okay, so this signals regime transition, which is important when say you include forcing in some atmospheric models or ocean climate ocean atmosphere coupled models. Okay. So now we go to the formal asymptotics or the homogenization process. By the way, the homogenization is also called second order perturbation theory or perturbation expansion. So if you're more familiar with that term, these are the same. Okay. So again, from the set of ODE, we get its associated. In this case, this is a Louisville. Okay. Sorry, this is a backward equation because we use the backward operator. All right. So this is its associated backward system, and L can be decomposed into terms with different time characteristics. So one with 1 over epsilon squared, one with 1 over epsilon, and then 1 over epsilon to the 0 actually. Okay. And then you just collect the associated All right, operators, okay, to those time characteristics. So for 1 over epsilon squared, just look at those terms. So those are from the subsystem, right? So g of y represents the right-hand side, okay, without the 1 over epsilon squared. And then the partial, and the gradient with respect to y is uh, is the vector of partial derivative with respect to y1, y2, and y3. Okay. And then L1 is associated with the time characteristic 1 over epsilon. Okay. So that is actually 4 over 90 y2. And then partial with respect to x. Okay. And then L2 is associated with 1 over epsilon to the 0. So that is your, oh, this should be just x, not x2, sorry. All right. All right. So I copied the operators here. Sorry, the backward equation here. And then we will assume that V can be written, or it can be expanded into V0 plus epsilon V1 plus epsilon squared V2. All right, in here, V0 are, are also functions of x, y, t, but later on we will see that V1 and V2 also, and the succeeding Vs. But later we will see that we can eliminate y in one of the functions. Okay, so if you apply the operators and collect terms with the same characteristic timescale, so just use this right-hand side of L and put that here, and then expand, and then collect all terms with 1 over epsilon squared from the left side and the right side. You will get L0 V0 equals 0. And then if you collect all terms with 1 over epsilon from the left side and the right side, then you will have this equation. And then finally, okay, those without any epsilon or have a characteristic timescale epsilon to the 0 gives you this equation. Okay, I will do some manipulations, and I will tell later why I am doing those manipulations in these operators. By the way, I'm leaving some technical details as I have seen in the introduction. So there are some smoothness conditions that these functions must satisfy, but we will not discuss that because it will take a lot of time. Okay, so this is the system of the operators that we have seen. So from the first equation, L0 V0 equals 0, maybe we should label this by 1, 2, 3 for easy reference. So from 1, okay, L0 V0 equals 0 gives you V0 equals a function of xt. Okay, so that means it is independent of y, or y1, y2, y3. Okay, that is not difficult to see because L0 is this operator. So if you apply the operator and take the partial with respect to y and gives you 0, so that means it has no y. Okay, or V0 is independent of y. So that's why its derivative is 0. So V0 is only in terms of x and t. Okay. From the second equation, you can compute V1 from here. Why are we computing V1? Because we will use that for the third equation. Okay. Again, there are some technicalities about this inverse operator L0 inverse. Now, if you're not familiar, if you're not that familiar with operators, you can just think of them as functions. Okay, then you can solve for V1 and just take the inverse of L0 and apply that to both sides. And you will get this form for V1. And then finally, okay, if you substitute that for 3, then you will get this equation, okay? Which I copied in the next slide. Okay, so this is the operator. So if you look at the operator, sorry, the resulting equation, the equation only involves V0 on the right side, and we want that because V0 is only in terms of x and t, right? Our goal is to eliminate y, okay? But the left side includes V2, okay? So there must be some way that we can do away with that problem, okay? With the existence of V2 there. We haven't done averaging, the averaging part in homogenization, expectation part when you talk about stochastic homogenization because we will be taking the integral with respect to an invariant density function. Okay. So our system is special in the sense that the fast subsystem has an invariant density function, rho infinity. What is invariant density? I will explain this in the most layman manner, maybe. Okay. If you run the model for a very long time, and look at the ensembles at one time, okay. At some point in time, the density at that time towards the and time after that does not change anymore. That's why it's invariant. Okay? And that is the invariant density of the fuzzy system. It is shown that the Lorentz interruptors invariant density. Okay? So if you take the expectation or integrate this with respect to the invariant density, okay, the left side becomes 0. The expectation of okay, L0 V2 okay, with respect to the density is 0. Okay, this is because the invariant density solves yeah, this is true. Okay, if you apply the adjoint operator, okay, to the invariant density, it will give you 0. Okay. Mm, okay. Why is that the case? If you go back to the operators, we are using the backward equation, and backward equation. Okay, the operator in the backward equation has an adjoint, and its associated equation is in terms of density. Right? If you can still remember, I said that it gives you the evolution of the density. Okay. Since rho infinity is invariant, it is invariant. So this is rho infinity. Okay. Yeah. In any case, okay. Oh, I forgot the rho infinity. Okay, because of that adjoint operator, L0 V2 rho infinity, and then you can move this. This inner product is L2. If you care. No, this is 0. Sorry. If you use the definition of the adjoint, yeah, then that will become 0. And that is all actually true for any L0 VI. Okay. All right. So then the right side, so the partial with respect to V0 is independent of Y. So taking expectation with the density associated with Y gives you just that term. Same with the last term, okay? And then this is the most complicated part, okay? Because it will have this expectation, okay? So now this is a reduced operator. It is in terms of V0 alone. It actually describes the evolution of V0. Okay. It is reduced in the sense that now it doesn't include Y, okay, in the equation. And then take note that this is an approximation of V. V0 is only an approximation of V. If you go back to how we expand V, right? So we expand V as V0 plus epsilon V1 plus epsilon squared V0. So it is this is only as good as how small epsilon is. So in the limit, V is V0, as epsilon goes to 0. Okay, so it's associated SDE. So now from the backward equation, backward Kolmogorov equation, we go back to its SDE counterpart. Okay, so it retains the drift part, x times 1 minus x squared, and then that part, okay, the second part that involves the expectation gives you a formula for sigma, or the diffusion part of the SDE. Okay, so we have eliminated y, but take note that this is only as good as how small epsilon is. We are not done yet because we don't know this part. Okay, so if we want to solve this numerically, then we must know what the action of the inverse of L0 is in the system. Okay, I will not discuss what that is. Okay, but I will tell you that that is just a negative of the area under the correlation function of y2. So you can you can run the system, okay, and then save the data for y2, and then graph its ACF, and you can compute numerically its area using some quadrature rule. And that will give you, take its negative, and that will give you that expectation. So then sigma squared over 2 will be a positive number. You can compute sigma from there. I tried to do this part for epsilon equals 0.1. So intentionally, I do epsilon equals 0.1. This is a weaker time scale separation. So then I expect that my approximation is not that good. Okay. In the paper, they use epsilon equals, oh no, they use epsilon, I think 0.01, yes. 1 order of magnitude, and they have almost a perfect fit for the PDF. So the right diagram gives you the PDF of the full system. That is when I run the system, including the y variables, and the reduced system. That is my stochastic differential equation. Okay, where I estimate the parameter sigma. Okay, and however, their autocorrelation function seems to be, or the autocorrelation function of the reduced model. Okay, seems to be a good approximate of the full model. Okay. Yeah, that's it for the homogenization part. I will not show the trajectory. Of course, we know that they will not have the same trajectory. One is a stochastic model, and then one is a deterministic. The full model is a deterministic ODE. All right. So to summarize, to give you a little summary, so you start with an ODE. Usually systems are expressed as ODE or sometimes as DE. And then use either the backward or forward equation. And then you do either averaging or homogenization. In this, I have shown homogenization to have a reduced backward operator or reduced forward operator. And then, yeah, and then find its associated reduced ODE or SDE. So this is the usual path, okay, when you do stochastic homogenization. All right. Some things to be careful about. It is very reliant on the existence of ergodicity of a subsystem. That means ergodicity gives us the invariant density. Okay? Without that, we will not be successful in the reduction procedure, at least in this case. But there are papers that somehow use other measures and find a reduced model. And also, the entire process is valid on the condition that we have an infinite time scale separation, which is not realistic, okay? Especially for most processes in atmospheric and climate science. They have actually weak coupling in terms of time scale separations. And and models are, especially reduced models, they're very sensitive to estimated parameters. So those are some issues with this procedure. With the details I skip, if you want to know how to do it properly, then this is a good reference in general. So it includes also homogenization for other for PDs. So that is a good reference. I present you a simple system, but actually the same procedure is applied for a more realistic system. The computations will be, of course, more cumbersome, but they can be done. These are some related methods that builds upon the homogenization procedure. Stochastic mode reduction first replaces the fast system with an SDE before doing the homogenization process. They are applied even on, say, shallow water dynamics. So these are more close to reality systems. And then there's a seamless version for that. Seamless because, okay. Actually, seamless because rho infinity, okay. Integration with rho infinity is done numerically, and rho infinity can be just assumed to exist without knowing its properties. And the parameters can be estimated. The record parameters, they are actually used for realistic barotropic model. Basically, the atmosphere for the tropics, the realistic barotropic model. And another atmospheric GCM. I think they're from the same author. Related to that is maximum entropy approach. For the maximum entropy approach, then this, okay. This method first estimates the density or the distribution of the subgrid processes before doing everything that we've done. These are some papers that you can refer to if you want or interested with knowing what that is. Okay. Now, do I still have time?
Go, Jeric. Probably 5 minutes, then we proceed to question and answer.
All right. So I think I can go fast with here because the remaining methods are data-driven methods. You have the time series-based methods, AR1 and NARMAC. So I include them here. They are done in Laurent's 96 models. And then I will not explain fully what a Laurent's 96 model is. But it is a specially extended system. I use the same notation so that it is not difficult to follow. I use X for the slow variables or resolved variables, and Y for the unresolved variables. So what we want to eliminate is Y, okay, and just take its effect in forms of. So F here is a constant, and BK is the only part where Y enters the evolution for X, okay. Together with periodic boundary conditions, this is a schematic diagram for the model. Okay, so your X are your large scale variables, which are also slow because we introduced that 1 over epsilon parameter there. So we make Y fast variables. So for every X, there is an associated JYs. Okay, and the values of JYs, its averages, okay, affects the evolution through BK. So Y are defined on a smaller spatial scale, and Y are made to be fast because of the introduction of 1 over epsilon. Okay, the subgrid term is BK. Okay. So how are data-driven methods done for this system? Usually, okay. First, the system is solved numerically, and then save the data for BK. So in here, I replace BK by ZK. because just to differentiate, that CK results from numerical simulation. Okay, but CK actually is an estimate for BK. Okay. This is one way to estimate ZK. If you use Euler formula, okay, this part can be replaced by a higher order. So I make a note here for higher order integration method like RK. So our problem is how to find or an appropriate stochastic model for ZK. So I present you AR1 and NARMAX, okay, in the previous slides. So by AR1, okay, we mean a polynomial regression plus an AR1 noise process. So in the graph at the right, you have XK. Those are the range for XK and different realizations for BK. Okay. So P here is a polynomial, okay, least square polynomial, and EK represents the residuals. Okay, when we estimate BK by a polynomial. So EK then is an AR1 process. It's modeled as an AR1 process. Okay. For most stochastic parametrization scheme, this is the base method. So it should perform better than the polynomial regression plus AR1. Okay, and a more complicated okay, upgrade of that scheme is this one in RMAX. Okay, it is an ARMA autoregressive moving averages model. So it models ZK as an ARMA plus a nonlinear function of x plus actually a term including past values for x. That is where the n here, nonlinear part, and the exogenous variables x comes in the name. Okay. So I think there is nothing much in here. The most important part here is to estimate the parameters and to represent the model, especially for NARMAX, to represent the model properly, choose a proper order for PQ, okay, and a proper form for the nonlinear function. So these are the results for taken from the NARMAX paper. NARMAX paper compares its result with the polyr. Polyr is the polynomial plus the AR1 noise. And for the PDFs and the correlation and cross correlation functions for the resolved models, NARMAX performs better. Of course, it's their paper, so this should be better. Okay. Another data-driven method. So this is purely empirical. Okay. Instead of representing, so this is conditional Markov chain. Instead of representing them by, say, polynomial regression plus noise process or other time series models, BK is taken to be a Markov chain. Okay? So for a Markov chain to be determined, you must come up with estimates for the transition probabilities. It is called conditional Markov chain because it is the transition probabilities are not only dependent on the previous state of the subgrid term, but also on the state of the resolved variables xk. Okay. So this is the difference between the deterministic. So if you have a deterministic with a polynomial fit, then you have one value for BK and for a given x. For conditional Markov chain, you need to make bins. So you need to divide the interval for x, and then for each x range of values for x, then you have to create bins for BK that you will use to estimate the transitions. The dots here are the representative values for the estimates for the subgrid term. So once a transition happens and moves to that bin, then you use that value for BK for the next time step in numerical integration. That's basically this, okay? This part. And yeah. So the paper with conditional Markov chain compares its results with the AR1. So that's polynomial plus AR1. So again, as we see with the PDF and with the correlation and cross-correlation functions, there is a better fit with the conditional Markov chain process. Okay, some notes with the conditional Markov chain. The binning procedures, it is sensitive to the choice of the binning procedure. So you can make uniform bins or based on the values of standard deviations or percentile quantiles, etc. And the transition probabilities differ significantly. So, and also the computational cost increases with the added conditions. So if the one or two conditions does not suffice or gives you a good reduced model, adding one means exponentially increasing your cost of integration. So that's one drawback of that. I will skip this part and maybe make a note on this part. Okay, there are other other models that are in recent years. Most of the papers, a lot of papers are produced that uses deep learning. So I think this is a new trend. Even I am doing now, we're applying machine learning techniques in parametrization. We've done homogenization Markov chain in other time series based models, but now I am more focused on this because that's what my advisor wants. Anyway, I think I have no time discussing these issues. Thank you for listening, guys. Sirs, moms. I think I will end here.
Okay, thank you, Jeric. But siguro you can unshare your screen and we want to see you if okay lang. Also, those people in the Zoom meeting, you can share your videos para naman makita tayo ng mga audience sa Facebook. If it's okay.
I'm in my quarantine here. Okay lang ba, sir?
Okay lang yun. Hello, Jeric.
Hello
Okay.
po.
Hello. Yeah, mahaba na yung hair natin. Okay. Okay. Yeah, I think you can unshare your screen para makita tayo sa Facebook din yung mga videos natin.
Should I pause or should I? How do I stop sharing?
Stop sharing, yes. Okay. Hi, Jerry.
Hello
Yeah.
po.
Hi, Jerry.
Hello po.
Hello, si Ma'am Kayen. Hi, Mayang. Belated.
Belated happy birthday, Mike.
Hello!
Okay.
Ang init sa Pilipinas. Grabe.
I know.
Uy, humaba na rin yung buhok ni Jeric, ni Jomar.
Sobrang haba na ito.
Kulot na. Okay, we can start the open forum. Baka may question kayo. Mayang, I know.
Meron akong question.
Yes.
Hello,
Yes,
Jeric.
ma'am. Hello po.
Yeah, hello. Yeah, well, you look great. Where are you now?
Thank you po. Houston po.
Wow, bongga, Houston. Regards sa mga Texan people.
Si Ma'am Kayen.
Yeah, so I really like the your talk about yung homogenization and of course it appears to me na for example dun sa example mo you said na yung parang yung chaotic system like which is an ODE system
Yes po.
you made approximation out from that, right? Like with SDE.
Yes po.
SDE is my field. It's been a while na hindi ko yan siya na-touch dahil marami akong ginagawang other things. Pero I'm just wondering, kasi I know that the chaotic system, ay sensitive siya sa initial condition, di ba? Like,
Yes,
yung
ma'am.
isang property ng chaotic system. So, sensitive dependence on initial condition. I'm just wondering if your theory has something to say about how initial conditions affect stochastic dynamics. Kasi, ang nangyayari, when you're approximating it to SDE, what you will be concerned about is yung distribution, long-term actually na distribution. Kaya nga, di ba, yung ergodicity, masatisfy yan. I'm just wondering if paano yung initial condition? Kasi yun yung signature ng chaos eh. Nakaka-capture ba yun doon sa SDE if we do that? And syempre, I understand na it should depend on the epsilon, di ba? Like, the smaller the epsilon, the better way of capturing it. I think it makes sense because in your system, I'm not sure about that. So, teka lang, kasi merong 1 over epsilon, di ba? Sa latter part. Tapos yung tatlong y mo, yun yung Lorentz. Yun yung Lorentz
Yes,
system. Tama?
Lorentz scaled with
Yeah, so
1 over epsilon squared.
the smaller the epsilon in your dx part, right? So even if you just look at the x dynamics, so kung small si epsilon, meaning yung 1 over epsilon ay big, so
Yes,
yung whole stochastic, dynamics, sorry, not just stochastic, pero yung dynamics ng x will fully be described by the chaotic part of the system. So in a sense, you can think of yung x mo as a chaotic variable, no? So ang iniisip ko ba na, okay, now that we have this understanding na pwede palang ganunin na you have a, sabihin natin, a fluctuating system which is really brought by chaos, tapos i-approximate siya in a stochastic sense, nawawala ba yung ang iniisip ko, nawawala ba yung SDIC na property ng chaos? And I think sana hindi siya mawala kasi yun yung yung important na part kasi yung butterfly effect, di ba? Like nakaka-capture ba yan still with your stochastic dynamics. So I don't know if I'm clear to you, pero yun yung parang nagko-question ako while you are presenting. Yeah.
Yes, I understand the question. So especially with the Lorentz system, so very close, even with very close initial conditions, they can diverge pretty fast. Unfortunately, with the reduction procedures, even with more complicated models, because the use of the chaotic system, at least in the paper, they are meant really to mimic a noise. So each dynamic doesn't matter, and it can be changed by other chaotic system, and the derivation will not be, well, the estimated parameters will be different because you have a different chaotic system. But in the derivation, mostly the parameters are dependent on the correlation functions.
Correlation nga, oo.
Yeah, autocorrelation functions, not on the paths that the chaotic system takes. So
I see.
yeah, so even if you have different paths for the chaotic system, they have the same autocorrelation function. So that part is lost, unfortunately.
Okay. Thank you.
So only the statistics they are chaotic. I mean, in the path, sorry, in the point-wise sense or pathwise sense, but their stationary statistics are well behaved. I mean, well approximated.
Yeah, kasi yung expectation mo nagda-depend siya actually sa Y2 na part siya ng Lorentz. Pero pakul ba siya doon sa Y1 and Y3? Kaya nga iniisip ko ba na what if you vary initial condition, how does your stochastic dynamics change if you do that? Like if you change yung initial conditions mo, tulad ng Lorentz, because in the long run you will actually see a different pattern somehow. So I'm actually wondering kung baka merong mangyayari, sabihin natin sa spectrum. Iniisip ko kasi yung spectra, although pinakita mo na yung autocorrelation function mo. I have another question for that. Yung autocorrelation function mo ba ay analytically, hence you have like smoother curve, or you just computed that numerically?
That's numerical.
Numerical. Okay.
Yes. Yeah. No, they're not sensitive to initial conditions of the full model because it only enters as correlations. So even with different initial conditions, they will have the same correlation function.
Yeah.
That's property of chaotic system. This chaotic system, because this is an invariant distribution. So yun po. So it doesn't depend. It doesn't depend on that. There are systems even that are kicked by some SDs, more complicated SDs, or even more chaotic systems. But after homogenization procedures, correlations or other time-dependent stationary statistics are involved, are the only ones involved in the reduced model. So it doesn't matter. when talking about the reduced.
Reduced system. Yeah. Thank you.
Okay. Other questions?
Ako siguro.
Makabit. Sige,
Yes po,
Makabit.
ma'am.
Homogenization kasi. Sabi ko, nag-homogenization na pala si Jeric. Hindi ko alam. Naisip ko tuloy yung ismama natin nakatulong sa'yo.
Yes nga, ma'am.
Nakatulong sa'yo ng ano. But anyway, nakita ko naman na actually it's not really the problem yung homogenization, but it's a way of
Yes po.
reducing yung SDE, no? So, tingin ko marami pang ibang approaches na katulad ng sinabi mo towards the end.
Mathematically rigorous po.
So, well, yung techniques ba sa mga paper, yung asymptotic expansion lang or enough na yon? Kasi especially numerical naman yung ginagawa
Yes po. Actually, the procedure itself po laging asymptotic assumption, either first order or second order.
Enough na siya.
Yes po. But on realistic models po, they introduce the epsilon parameter to do the homogenization. Yeah,
So
kasi,
kaya siya pwede kasi yung fast slow
yes po.
scale
So they are intentionally made to be fast. when and then usually in-adjust lang po yung parameter. So once computed na po yung parameters na they are usually adjusted because well the assumption is wrong. I mean, they are not usually that have scale separation at the start. The epsilon parameter is only introduced just to do the homogenization process.
Para magamit. Kasi nga approximate. So ang idea kasi ng homogenization ay ma-approximate talaga yung ma-approximate yung effective property ng material by looking at the composite as a homogenized one. Pero hindi naman talaga ganon. Heterogeneous talaga yung material. Pero syempre may malulus na something when you make it homogenized, or yun nga when epsilon goes to 0. So yun yung mixed na siya. Yun yung idea. So yun nga parang may mawawala in some sense. Hindi ako familiar sa SDE homogenization, pero sa deterministic homogenization, so yun yung malimit na tanong. So gaano ka na-approximate nung iyong bagong coefficient yung talagang property nung say material. Pero dahil lang itong example na diniscuss mo ay pwedeng gamitan ng homogenization kaya siya pumasok Pero parang maganda yung isa mo pang ginagawa yung sa deep machine
machine learning po. Actually yung current kong project po ay sa machine learning.
Okay. So yun lang.
Yun po kasi yung funded.
Na-appreciate ko lang na, pwede para talaga rin siyang magamit in that sense. So, hindi ko siya na-try pa before on SDEs. Lagi kasing for deterministic PDEs yun. Pero the idea naman is the same.
Yeah, it's the same.
Sa averaging.
Only that instead of for composite material, you have the additional x over epsilon.
X over epsilon.
Para sa space po. This time when you have a slow fast system, because it is on time.
So nasa labas.
It goes out.
1 over epsilon or 1 over epsilon squared. Okay. Pero sa homogenization nga, x over epsilon siya. Yung
it enters the space variable. But the procedure is almost the same.
The same. Okay, so tingnan natin. Baka meron tayong pwedeng magawa when you go back.
Okay. May questions po? Ako may question, Jeric.
Go, sir.
Ayun. Balik tayo dun sa may chaotic system.
Yes po.
Definitely, parang ilalagay ko lang siguro sa, let's say we put physical interpretation. So parang yung the deterministic part ng ODE without the noise is like, let's say the average, let's say the macro scale. Okay? Tapos when you go to like the micro scale, syempre may mga noise doon. So that will, yun yung pupunta dun sa ano, 'di ba, sa noise part. And the epsilon actually gaano siya kaliit would determine how micro the scale is na kinokopol mo dun sa deterministic part. Pero
yes.
Usually may posibleng may ma-miss na ano ba yung nasa gitna, mesoscale, parang gano'n, di ba? So parang pag nilakihan mo yung epsilon mo, definitely pwedeng mesoscale. Kaya lang the problem doon is posibleng masira yung math, di ba, later, kasi when we make epsilon approach 0, that would be easier sa math. Now, ang question ko dito is sinabi ko lang yon kung tama ba yung pagkaka-interpret ko physically. Pero dun sa figure mo kanina na meron ka ng distribution kung saan pupunta yung state, 'di ba, pwedeng -1, 1, mas mataas yung kanyang peak compared dun sa 0 kasi unstable naman yung 0. Now, meron bang case na magkaroon ako ng noise na biased in the sense that, kasi parang tinignan ko kanina magka-same height yung negative 1 iniisip ko, kung nag-start ako ng, kasi deterministically, pag nag-start ako ng malapit sa negative 1, dapat doon ako pupunta. And I expect na kahit may noise yon, mas mataas dapat yung peak doon negative 1 ko. Pwede ko bang iusod yung aking dynamics na hindi masyadong maapektuhan ng noise ko, yung dynamics na yon, na such that mas mataas yung mode ko doon sa negative 1?
Yes, sir. I-vary niya lang po yung potential. Yung function x minus x cubed. Yeah. I-vary niya lang po yung coefficients. And then, actually, not coefficients. Mag-add po kayo ng isang term na pwedeng mag-iba yung shape ng double well. In this case, double well lang po siya. Pero pwede niyo siyang ibahin. Pero usually, it does not take into account your initial condition, just how deep the wells are.
Okay.
So kung mas deep yung isa, mas mahirap po siyang i-kick ng noise kaysa dun sa mas mababaw na deep. So the PDF will be unimodal, not bimodal.
Okay. Yeah.
So, ibabari lang po yung potential. Just to actually, pwedeng isa lang siyang potential, but then you have a multiplicative noise. Pag multiplicative noise po kasi siya, mas madali siyang i-kick sa state. Halimbawa po ito yung well niya. And then you have multiplicative noise, and these are the positive values. So kung dependent po siya sa positive noise, mas malaki na positive number and multiplied to a noise, mas nakikick siya when you go to the positive side. So nagko-cause din po yun ng mga peaks sa PDF. So either you add the multiplicative noise, mas madali po siyang kontrolin with multiplicative noise if that is the end goal. Then adding a term and varying the potential.
Okay. Yep. Thank you, Jeric. Are there other questions po? Sa Facebook, wala. Walang nagtatanong. Pero maraming nagwa-watch. Okay? Kanino umabot tayo ng 30 plus. That's good. Okay. Are there other questions po?
Meron pa akong question.
Go, Maya.
Yes, ma'am.
Sorry, I really like this stuff.
Yes, ma'am. Gusto ko po yung mga questions.
So, balik tayo doon sa ODE ba? Kasi you need an ODE na para na merong fast and slow siya, di ba, na system. And
Yeah,
yung example mo ay, tama ba ako?
Yes,
merong
yes.
may separation of time scale, for example, sa ODE.
Yes.
So, necessary ba na fluctuating yung ODE mo dapat in order to apply itong approximation to stochastic differential equation? Kasi you could also choose an ODE na medyo smooth siya in the long run and then mag-iba lang siya na time scale. Like, or necessary ba talaga na may fluctuation?
Hindi po necessary. Kahit ano po yung kahit ano po yung form ng function na in X alone.
So that is very interesting kasi okay, so kasi di ba sinimulate mo yung trajectory ng X and then it shows like a jump process, like going like that and then may fluctuation. So for example, hindi sabihin natin like a limit cycle kind of thing. A limit cycle na na situation, ibang time scale lang siya. So sabihin natin ang limit cycle ang nagda-drive sa X instead na chaotic system ang nagda-drive sa X. And then i-convert mo siya to SDE. Kasi ang mangyayari sa SDE kasi for sure merong fluctuation eh.
Yes po.
Yun yung parang worry ko. Kasi ang ginagawa natin, if we want to use yung stochastic na statistics sa pag-compare, clearly mawala talaga yung parang effect ng fluctuation kasi ang kino-compare mo lang is yung average dynamics eh, kasi you have to repeatedly like simulate it. It's what I'm trying to say is that what it captures really is yung deterministic aspect. Kaya yung PDF mo ay sort of similar or close to each other because mas kinakapture niya yung deterministic aspect
yes.
System mo. So parang feeling ko parang walang effect yung mga sigma BW, parang kung ganun yung magiging natin comparison. So I'm just wondering like I think what you're really trying to do is really capturing yung deterministic aspect. So hindi ko mag-gets kung if we want to do all this nitty-gritty detail and then by the end of the day when you apply yung comparison, ang makaka-capture mo ay yung deterministic aspect. So ano yung point ng approximation?
Yes po. Okay. Well, with the system, okay. Mag-start po ako sa system na to kasi siya yung maganda example. When you take out the kicked, the PDF will be either Dirac at 1 or -1. So that is really necessary in this system. But your question po is what if I have a smoother function? And then and like a weaker
variance.
kicks.
That's the reason.
Weaker kicks po. Then it will be dominated by
the deterministic.
By the deterministic po. And honestly po, for those part, yung deterministic parametrization works fine. Kasi po maliit lang po yung spread niya.
Yeah.
Maliit lang yung spread niya because of maliit na because of small fluctuations. So deterministic works pretty well with that. So with that, that means stochastic homogenization is not really necessary. It can be really an additive noise.
Yeah.
Usually when we do stochastic homogenization, our point of comparisons are the deterministic model, the one without the subgrid term. So we eliminate that. And then the one with the mean of the subgrid term. So that is also deterministic. And then the one with an additive noise.
Yep.
So if it performs really well, even with the small additive noise, then maybe the homogenization part, because usually for more complex system, after homogenization, it doesn't only involve additive noise. It involves a multiplicative noise of some form with different parameters. It really is messy, especially if you have a lot of variables and an additive noise. So usually po, kino-compare namin siya sa mga, and we see, and we look at the contributions of additional terms if they are good correctors with the system that you just truncate the kicks.
Right. Okay.
So ina-analyze na lang po namin siya when the correction terms are are really helpful, at least in estimating statistics. So it's really system dependent po.
System dependent nga siya. Sige. Thank you.
Yeah.
Okay. Siguro we had a wonderful morning with starting the morning with mathematics. Okay. So siguro mag-end tayo dito, but before we end, may I ask Dr. Edita Jose to say some closing remarks? May closing remarks tayo ngayon.
No problem.
Okay, so thank you sa lahat ng organizers of this, how do you call, 1UP webinar. So this will be the start. So who will be the next one?
Ang schedule natin ay UP Diliman, but we're going to announce the details later. Then ang susunod niyan ay UP Mindanao, and then sunod-sunod siya.
Yes.
So 1UP to. We're
Yes.
united for applied math.
Okay, so weekly webinar. So this is a nice idea, great idea, no? So while we are in lockdown, and let us take the chance to this opportunity to share our research. So siguro maganda rin na next time yung COVID updates naman yung ating i-share, no? 'Di ba? I think maganda rin 'yon.
Si Jomar na yan, Jomar.
So maganda rin na
nakasawa na yung COVID.
maganda rin na hindi na we started not with a COVID topic. Pero I mean, we have to I think share those kasi nababasa lang natin, pero we want to hear it from the group or from the response team also. So salamat sa lahat ng nag-join. So we hope to have more views next time, 30 sa Facebook. So let us have more, let us advertise more. And I think hindi lang naman math community, no? So we can also invite stat people, physics people. Kasi halimbawa itong SDEs, no? So I think they can also relate. Who knows? So let us invite more. And again, thank you sa ang main organizer si Jomar. Si Jomar ba ang pasimuno? Sige. So salamat ng marami sa lahat ng nag-join sa atin this morning.
Thank you, Ma'am Edith, and thank you for the viewers. This video will be posted permanently sa Facebook, so you can watch Jeric kahit kailan, kahit pwede nyo ulit-ulitin. And also this will be posted sa we're going to create a 1UP YouTube channel, and all of the videos will be there. Okay ba, Jeric? Okay.
Wala na po ako magagawa.
Okay, thank you very much. Thank you very much.
Magka 10,000 subscribers tayo, so magkakating
tayo, may pang-test kits na. Kung hindi man natin kayang mag-suggest, mag-improve ng model, mag-test kits na lang tayo. May test labs na dyan sa may pambili natin ng mga testing kits.
Okay, sige. Thank you very much. Bye-bye. Bye-bye.
Thank you. Bye-bye.
Bye, Ma'am Kaya.
Bye, everyone. Good job, Jeric. Bye.
Thanks for watching.